Hi, I want to talk about the physics of diffraction gratings. Now, with diffraction, when we talk about that as an effect, it's usually a wave encountering a single opening. If we have multiple openings, then technically we're talking about interference, though, as we mentioned earlier in the chapter, diffraction can be explained in terms of wave interference. So, what happens with the diffraction grating is we end up having many openings. Hundreds of openings per millimeter usually, or more. So what would happen with a single slit diffraction pattern is that we would see a center bright region and then bright regions off to the side with a dark region in between each because of the nodes of that diffraction. Now, if we have two slits, we get an interference pattern where we see alternating bright and dark lines, but the whole pattern fades out at the dark region of our interference pattern, and then we get more fringes in the next bright region, pattern goes away, more fringes, pattern goes away, and so on until we run out of visibility. Well, as we start adding more openings, if we go to 3 openings instead of 2, what we end up seeing is an alternating pattern in the fringes, where we have a dimmer fringe and a brighter fringe, a dimmer fringe and a brighter fringe. If I go to 4 openings, I get 2 dimmer fringes in between the bright fringes. Every time I add a new opening, the dim fringes get dimmer, the bright fringes get brighter, and we get more of those dim fringes in between. And by the time we get to a diffraction grating, where we have n lines per meter, where n is usually in the tens to hundreds of thousands, then the spacing of the lines is so close in terms of the openings that really we can only calculate constructive interference from neighboring sources. So there's going to be some separation distance d in between those lines. Well, the separation distance between the lines is going to be the width of our diffraction grating divided by the number of lines that makes up our diffraction grating, or it's going to be 1 over the number of lines per meter if that's what we're given for our diffraction grating. So from constructive interference, we're getting an extra amount of path that's equal to our spacing of openings times the sine of our angle out to where our bright fringes are going to be. That's going to be equal to an integer number of wavelengths. And with diffraction gratings, the angles we're talking about are almost always large from the beginning. So this isn't something where we're going to use approximations. We're going to have to use arc sines or the sine -1 function in order to figure out what our angles are going to be. So say we're shining 589 nanometer light on a diffraction grating that's 20 millimeters wide and has 6,000 lined openings in that 20 millimeters. So the first thing that I like to do when I'm solving for these angles is I take a look at the argument that's going to be inside my arc sine. So if the sine of theta is going to be an integer times my wavelength divided by the separation distance between spaces, so that separation distance between spaces is going to be the width of our diffraction grating divided by the number of lines. 1 over that is going to give me the number of lines divided by my width. So I'm going to take a look at this piece right here, because if it's greater than 1, we're done. We don't have any extra fringes other than the center bright fringe coming through that grating. So if I take a look at that center piece, 6,000 lines times 5.89 times 10 to the minus 7 meters divided by a width of 20 millimeters, which is 0.02 meters, gives me a value of 0.1767. And 1 over 0.1767 gives me 5 point... I don't care about the decimal place, because this is a truncation situation, right? Once we hit 1, there is no solution to the inverse sine that exists on the real number plane. So, real number line. Complex plane, yeah, we have some solutions there, but we're dealing in the real world, the physical world. Once we hit 1, we're done with our sine. So, in terms of our pattern, we'd see a center bright spot and then 5 bright spots above and below that center bright spot as the light passes through the grating. So I'd start by taking the inverse sine of 0.1767, and that gives me an angle of 10.2 degrees, and it would be above and below the center. We get 20.7 degrees. If I take 2 times 0.1767, find the inverse sine of that. 3 times is going to give me an angle of 32 degrees. 4 times that value will give me an angle of 45 degrees. And the last value I get, 5 times 0.1767, gives me a number in the upper mid 8s, like 0.88ish. And the inverse sine of that value is going to give me plus or minus 62.1 degrees. Thanks for watching.